Looks like we're recording, so I'll just start sharing my screen now. All right, so welcome. Okay. I thought it was mine. Okay, welcome, and today I'll just be going over the basics for machine learning with the method of linear regression. So to start off, let's ask, what is machine learning? Machine learning allows computers to learn without being explicitly programmed. So when given new information, they should be able to complete the task assigned to them, even though they weren't initially programmed to deal with that sort of data. Another definition for machine learning could be a computer program which learns from experience with respect to some task and some performance measure. All right. Examples of machine learning would include classifying emails as spam, autonomous vehicles, handwriting recognition. These are all various types of machine learning, and they are accomplished, these tasks are accomplished using different algorithms or methods for machine learning, such as supervised learning, unsupervised learning, and reinforcement learning, to name a few.
No, I think my sound might be. Oh, no.
Yeah, I don't think you need the volume on.
Yeah, I don't think we need the volume through here.
Yeah, I'm just wondering if it's recording.
Okay. All right. So linear regression is a form of supervised learning, meaning that.
Oh. Yeah. sorry.
Okay. All right. Linear regression is a form of supervised learning, which essentially means that a hypothesis function is induced from a data set with labeled examples. So a data set with X inputs and Y outputs. The outputs are known, and like we know essentially what it should look like. And with regression, this means that we're dealing with continuous values as opposed to discrete. Examples include predicting amount of rainfall for the upcoming stormy season, given the data from previous years, as well as predicting the price of a house given its size in square feet. So over on the side, you can see you have X square size in square feet on the X axis and its price in dollars. And this is basically just a little visualization of a data set that can be used in linear regression. So here's some standard notation to help that's useful throughout this presentation. For one, we have M, which is number of training examples. X is an input variable and Y is the output variable. So to better contextualize this, here's XI and YI. This just stands for the ith training example. And for example, X2 and Y2 would be over here, 1,416 and $232, and price in the 1000s. So if you were to do that for the X4, it would be this 852. That's the fourth X value. And then just to clarify, each of these X and Y values are a training example. So what is a hypothesis? A hypothesis function is what is produced by the learning algorithm to help classify or classify your data. And it is a training set is used in your learning algorithms or in the linear regression in order to induce this hypothesis. In linear regression, a standard hypothesis looks like this function over here, which is theta 0 and theta 1 times x, kind of like y equals b plus mx. I know it's usually mx plus b, but given this form, theta 0 plus theta 1x, it's similar to b plus mx. So for example, you would have a h of x would look like this green line over here, and that would be like the hypothesis function. So you would be able to essentially say if my house is about like in here in between 500 and 1000 square feet, so like 750 square feet, you'd be able to go up to the to this line, the green line, and show, can I get a, yeah, just to make it a little clearer. Yeah, you'd be able to show that the price should be about $100,000. Yeah. Okay. So parameters, as you saw before, there's theta 0 and theta 1. These are essentially like the weights for this, for the linear regression, and given the values is the values of these parameters is what essentially makes the line, the h of x line. So for example, if you had theta 0 and theta 1 equal to 2 and 0 respectively, you would get this line over here. Hope it's coming out clear. I'm not sure if I should annotate. It's clear?
No, yeah,
Okay.
yeah.
All right. And then if you have a theta 0, so, oh, and also to clarify, theta 0 would be this value right here, and then there'd be no slope, so it's just a flat line. And then going over here again, you have a theta 0 equals 2, while theta 1 equals 0.5. And the 0.5 essentially is the slope. So theta 1 is in charge of the slope in this case. And you have a line that comes out like this. And then finally, you have for this data set, the h of x, which fits this data set the best, which is theta 0 equals 0, while the theta 1 equals 1. So you have a nice line that fits the data value, the values perfectly. And the goal for linear regression is to choose theta 0 and theta 1 so that h of x is close to the actual output y. Now, the cost function helps us determine how close the hypothesis function is to the actual value. And it can also be used to like help change the theta 0 and theta 1 values, but we'll touch on that a little bit later. But here we have the cost function, which if you look at it closely, you have for every value, for every training example, you want to compare or like find a difference between h theta and h of and y, the actual output, square it and divide it by the mean. Well, this is basically a mean squared error if you want to get technical with the math. But the goal, you would want to minimize this cost function, and I'll explain that or like illustrate that in the next slide. So here with the same graphs that we had from before, you have your theta, the same theta 0 as theta 1. And if you were to go through the calculation using the previous equation, you would calculate these values for the cost function for each graph. So here you have a cost function, which is equal to 1/3 essentially. So it's like kind of okay. Then you have like the second graph, which is 0.58, about 0.6 cost function, which is, not the best area. It's not really what you want to see with your h of theta. And then finally you have the cost function equal to 0. And that's basically when your h of theta aligns with the actual output. So that's what we want to do when we're doing the linear regression. Now, gradient descent is the process by which the cost function is optimized. So here we have theta. This is essentially an update of the parameters. Here theta j, oh, I should use this. Here theta j, the new theta j is set to the current value of that theta minus this, partial derivative of j theta of the cost function and times this alpha, which is essentially the learning rate. And for clarification, j theta just can be 0 or 1 in this case. So like down below we have the respective values or the respective gradient descent for the theta 0 and theta 1. Notice how theta 1 requires you to multiply by the x value. That this x value is whatever the ith xi, so like if you have x2, whatever that x2 value is, you would want to multiply by this by h of the difference between h of theta and y. Also notice how the partial derivative of this function, like that's, here, let me, yes. This partial derivative is really just, if you do the chain rule, I believe, for the cost function, you're gonna get this value. So, yeah. Okay, and here's another visualization of your gradient descent just to make it clear. So on these values, or on these axes, we have theta 1 and theta 0. And then you have your cost function. So if you were to say have a theta 0 of 10 and a theta 1 of about -20, so along right here, your cost function, the value of your cost function would be up here, which just means the error is super high. So if you were to take the derivative of of the cost function, j theta 0 and theta 1, you would essentially, when that derivative is 0, that's the local minimum, yeah, essentially, or global minimum in this case. And this is usually what it looks like for linear regression. Yeah, this is just how it looks for a linear regression. And so and also notice, going back to the this gradient descent, when the partial derivative equals 0, there's not going to be any more updates to the weights. It'll just stay the same. And that's essentially when you get to convergence. So here's the linear regression approach, all in one slide. You want to, if you were to like implement this in whichever, whether it's MATLAB, Octave, or Python, whatever you want to use, you would want to make sure that you set the appropriate parameters. Just to know, alpha is usually way smaller than 1. The smaller the alpha, the slower the more time it takes to converge, but you're more likely to get a convergence because if you have too large of an alpha or a learning rate, there's a chance that you might just jump around and never just get to the minimized cost function. And then you want to set theta 0 and theta 1. You can really set them to anything, but like you could set it to 0 and 0 just to start up. It doesn't really matter because the gradient descent is going, well, I won't say it doesn't matter. I'm sure there are like algorithms or like studies that say like this weight is the best or this parameter is the best, but like I won't get into that. Just to like start off, you can just have 0 and 0 for your parameters. Then you want to perform gradient descent by calculating the partial derivative of the cost function. find the new values for theta 0 and theta 1, set the current theta values to the new ones. And this change has to be simultaneous. You can't do it one after the other. And then repeat until convergence. And then finally, you get your hypothesis function, and you can use the hypothesis function to predict new values. That's basically the linear regression approach. So, if anybody, yeah, if anybody has any questions, yeah.
I'm wondering, like, how would you do it simultaneously?
Okay. Yeah, I think it might be different in different like program languages, but like I don't have the actual here. I'll just try and explain it with this right here. There are better oh wait, no, I think I do. Well, the point is the reason you want to do it simultaneously is because if you were to update your values like one after the other, then the value of this cost function would be different. But to do that, you would just find, this partial derivative of the cost function and then use it, like set that as a variable, and then basically do what you see right here. I'm sorry, I know that wasn't the best explanation. Maybe I can share like one of my other screens. I also don't know if this is going to make too much sense because it is MATLAB. And like, I'm not sure how familiar you are with MATLAB. But say, for example.
Oh, no, yeah. So I thought like you weren't even doing it before. Like, I was like, how do you do it better?
I wanted to keep it simple because I'm not sure how familiar everybody is with MATLAB. And like, you need to also know about like matrix, linear algebra. Like I didn't want to like have to do a whole introduction to MATLAB and linear algebra and the linear regression. I just kind of wanted to keep it simple for just this part, but like I'm not sure if there's anything I could maybe explain to help with the understanding.
So you just like say the equation and just like code it out?
Yeah. Maybe for clarification, here's the partial derivative. And the values, the equation is slightly different just because, you have going back, oh, I'm not sharing the screen, but if you remember from the gradient descent, you need to just multiply by the x value of that current training example. Is there anything else I can say to maybe help clear things up if anybody has any questions? Hope I didn't go too fast. I feel like I might have rushed.
No question. So what exactly does convergence mean?
Okay, just meaning that like you get to the point where the cost function is minimized.
Okay, so like is that like 0?
Yeah.
Oh, okay. So the examples that you showed were like that function would go like 0.5, that would like never really happen then?
Yeah. Oh, okay, let me go back to the. Oh yeah. So essentially these would just be like different iterations of the gradient descent. So like say you start off with 2 and 0. Well, honestly.
Oh, yeah, wait, so so
yeah.
Does it just like consistently choose new data? So like it gets to the 0 point?
Yeah. So like you might start off with these parameters, and then it will go through a gradient descent, calculate that the cost it would calculate the partial derivative of the cost function, and then depending on like that value, it'll move closer to maybe like this next one to this next h of x, and then it would calculate the error again, and it'll keep on doing that, changing the parameters until you get to a cost function where that error is 0. Yeah. No, it's fine.
How are you choosing the data points that you're using? Like, how does it know, like, oh, well, here this 2 and 0.5? Like, how does it know how to switch?
You would want to provide a data set to train, these values, or to train with. So like maybe say this is X, the first training example, this X right here. You would go through that process, calculate the error, and then you might you would change it again. Like you would change the parameters, and then go to the next.
The first one can be random. You can start
Yeah.
anywhere.
Or like, do you throw away the data? Like, do you ever like not use a data point?
Well, yeah, you can get into like, right now we have like a pretty good set of data. Like you might come to and be in a situation where your data might be clustered, or like maybe even a polynomial, and then you would want to have maybe a different approach to, like, you might want to use a polynomial regression as opposed to linear regression. Did that answer your question? Like yeah.
If the data is clustered enough, you may do like 3 iterations and already minimize your cost function and you have your equation. Depends on the data set. If it's all over the place, it's gonna take you more tries.
Also, I feel like I should what's it called? I think I misspoke. You only change the parameters after you gone through all the training examples. So like with the current parameters, theta 0 and theta 1, you calculate the difference for the difference between the hypothesis function and the actual value for every single training example, and then you find the sum of that and divide by 2 times the amount of training examples, and that's how you get your cost. I think I misspoke. I'm not sure if I did. Any other questions? Did you want me to stop recording? Yeah. That is, I cannot, sorry. I'm not used to